So nobody can say, it's open to interpretation, everybody is right. So in those classes, everybody gets an A grade. If you show up, do the work, go present your research topic, write a good report, everybody gets an A grade because these are all opinion-based classes. What do you think about what Shakespeare thought when he wrote the Hamlet? Hey, I can write whatever I want. Shakespeare is not going to come and tell wrong. No, right? But when they come to my class, there are answers that are right and answers that are wrong. They can't say that, yeah, I think the angle of diffraction here is 70 degrees. So you don't think, it's either 35 or not. Nobody thinks, right? So you're more of fact-based, and when you're fact-based, make sure that you get the facts right. Like you see in TV here. Now, if there is nothing called an opinion-based stuff, can you go and sit in TV and argue like these politicians and this channel people argue in TV? That, no, I think this is that, this is that. No, you can't, because for you, there's only one answer. And that's the right answer. And nobody can, because what science tells you is the right answer. So, you get all these diffraction patterns, and sometimes, and I have gone through this while I was at IIT doing my master's 18, 19 years ago. I sent some samples over to the central X-ray facility. And in those days, it was all printout. And they sent me a printout. And then I had to go there and sit with the X-ray diffraction manuals. I don't know if any of you have seen those, where you will have the 2 theta values written in font 3, along with the possible combination of compounds for all those different things in reams and reams of paper. And you have to go through, scour through everything. You have to identify if there is silica, if there is magnesia, if there is alumina. They'll give you some random name of compounds. And in our collective ignorance, we write whatever we find first, because I don't have time to go through all of that. So I think I have silica. The first thing that has silica is what I write down. And then when you try to publish, you know that you're totally wrong. Now you have expert analysis software that will tell you, if you give it the software, the range of what you're looking for. And still a lot of people get it wrong. My students come with ridiculous materials that I can never form in cement paste. Just because there is silica, alumina and calcium doesn't mean anything that can be a combination of silica, alumina and calcium can be formed. Remember, thermodynamics tells you what can form and what cannot form. And that's why you need to know thermodynamics while you're analyzing these things also. So be a little careful when you are analyzing X-ray data. Again, conservatism is always good in these kinds of things. Okay, so representative peaks in a cement, hydrated cement paste, 28 days hydrated cement paste. Calcium hydroxide, you will always get this beautifully. Why? Calcium hydroxide is a real crystal. You will get calcium hydroxide really, really nicely. And if you do a pure cement paste, that is the only thing that you can guarantee that you have in your system based on XRD. That is it. If you have put in limestone, you will get calcium carbonate peaks that you can guarantee. If your gypsum has not reacted, you will get gypsum peaks that you can guarantee. If you are doing a mortar with quartz sand, you will get beautiful, so many peaks of quartz that you can guarantee. I would encourage you not to do X-ray diffraction of mortars if you have to understand what's in your cementitious system, because quartz masks a lot of other things. The quartz peaks are so large that even the other larger peaks seem very minuscule and you can't find out. So if you're interested in finding out, do always a paste, not a mortar. You will see a lot of people publishing X-ray diffraction results with mortars with full of Q all the way around, and they say, oh, we did a mortar, so all we find is sand. Of course, sand is crystalline. We haven't found out a way to make sand amorphous. So you will see all of that. No surprise at all. Do only a cement paste and be very careful about what you're looking at. Fly ash, if you put in fly ash, that's another danger now. If you have fly ash, you will apparently get a lot of quartz. If your fly ash has some iron content, you will get hematite. You will get cristobalite. You will get all those crazy things that you sometimes will mask it. So That is why if you know that where the quartz peaks are coming, there are ways to ignore those peaks and do the other areas if you want. And especially for fly ash based systems, slag is not that dangerous because slag reacts very quickly and gets you a lot of amorphous products back. But if you're doing fly ash, I would always, if you're interested in product quantification, I would always ask you to supplement XRD with SEM and EDX analysis. If you're really wanting to know what you have, SEM analysis with EDX is always required with fly ash. With plain cement paste, actually plain cement paste you don't have to do anything because you have so much of literature that tells you what's in there, right? So you really don't need to do it. But if you have to, that's very easy. But the other ones, anytime you put in more materials, more geopolymers, it gets very, very, very complicated. There's a lot of different things that can form in geopolymers. A simple example, when you have your sodium hydroxide concentration changed, right? Basically your sodium hydroxide, your sodium is just a lazy thing doing nothing. It's a hydroxide that's doing all the work. And your hydroxide gets more potent when it's associated with an alkali ion rather than with a neutral atom like water. Water also has a hydroxide if it starts to dissolve. But water doesn't dissociate as fast. It's not as ionic as you want it to be. But if you have a strong alkali metal associated with the hydroxide, it will dissociate very fast. So it's a hydroxide ions that's doing all the job. Hydroxide ions are really alkaline. Hydroxide ions start to dissociate the surface of fly ash, lets all the ions from the fly ash come back to solution. When that comes into solution, now basically if you remember your geopolymer mechanism of formation, basically you're forming a sodium aluminosilicate gel, NaSH, CaSH, whatever you call it. The sodium aluminosilicate gel is formed by a process where silica is replaced by alumina and the alkali cation, right? In the network structure, the tetrahedral silica structure, all of you remember the tetrahedral silica structure? Si4 plus. In that 4 plus, if I have aluminum, what's the coordination number of aluminum? What's the valency of aluminum? 3 plus, right? So if I take one silica off Si4 plus, and instead, because fly ash and slag are rich in alumina, one alumina goes in Al3 plus. Does it balance the structure? I am short of one positive charge. Where is that positive charge coming from? Na plus or K plus. That is a mechanism. So basically, sodium is this lazy guy hanging around trying to find out who is pushing the door open so that he can also run in and stay inside. That's what sodium is doing. And then, if he is waiting to go inside, you should know he is waiting to come out also. Right? That's why such systems with high sodium concentration leaches out. Anything that is so quick to go in, you should know, will be so quick to come out also. Because again, if a sodium ion can speak, the ion will come and tell you, I am also guided by energy considerations. I am waiting for, I am also a least energy guy like all of you. Somebody pushes the door, no energy waste, I went in. Somebody tried to push the door open out, no energy, I came out also. Right? Every material operates on the basis of energy minimization. Everything. And that's why if you do thermodynamic calculations, you will know what exactly will happen with these systems. Okay. Any questions on XRD? That's a more complex XRD of a paste with ettringite, quartz, dolomite, calcite, calcium carbonate, hydrate, portlandite. This is what you will have. This is kind of structure that you will end up with. If you don't really need a crystalline product identification, and some people do this, all I need is to know if my material is amorphous. And I have people tell me this. Why do you do XRD? Because you know what is in there. Oh, I want to check if my material is amorphous. You should be so insane to check if your cement paste is amorphous. Oh, if I'm getting the bump. You will get the bump. You will know what the bump looks like. You will say, this is the bump that you're talking of. You know it, right? So it's sometimes, if there's a fly sitting on your body, take a newspaper and swat the fly. Don't take a machine gun to kill the fly. Simple. These tools are expensive. Sometimes we in the concrete field think that we have to use all these sophisticated instruments that other chemical engineers and metallurgical engineers and other people who fabricate, manufacture new materials use. We don't have to. A lot of things we know. But if you have a new material, if you want to know what those crystals are, very good idea. Just to identify calcium hydroxide, don't even bother. And also, quantification by X-ray. How many of you have quantified anything in an X-ray? Very, very, very hard. You can do Rietveld refinement. You can do Rietveld refinement. You should have somebody who knows how to interpret your Rietveld refinement. Or you should sit and learn Rietveld refinement for 3 months before you do it. Rietveld refinement is not something that anybody, and then for Rietveld refinement, you just can't take your paste and do XRD. You have to dope it with some materials that will give you the right Rietveld signals. Right? So quantification by X-ray, and some people will do based on peak heights. Okay? I have done it in the past, long time ago. I regret doing it. Please don't do peak height based quantification, because peak height has nothing to do with the quantity. Peak height has only to do with the crystallinity of the phase that you have. If it's really, really, really crystalline, the peak will be strong. It does not mean that I have so much of calcium hydroxide, therefore I have all this big peak. No, peak height is a function of how crystalline your structure is, not how much you have. Okay? So be very careful when you do these techniques. Again, I'm giving you more of pitfalls than uses, because you guys know how to use this and you've used this, but it's important to know what the downsides are, right? In the US, if you have to get a motorcycle license, to get the car license is very easy, right? You can go, drive, take your car, drive. Some places they'll ask you to do parallel parking, right? When two vehicles in between parallel parking, there's a science to do parallel parking, which I learned the hard way. So you actually drive all the way to the front door of the vehicle there, and then come straight back again and turn right or left depending on which side of the road you are, right when the bonnet of your car reaches the edge of the other car. And then turn it completely, and when you almost get to the corner, straighten up, come back, you will park nicely. Real nice science, no ambiguity, right? They've even made it into a science. And there'll be space between two cars, not like Bombay where you have to push that car with your car to get space, which I've seen people do. Or the auto guy goes in and pushes that guy in and puts his car in. No, you don't have to do that. So like that, you have to do some nice science in order to understand what these are. When I'm doing more of pitfalls so that you are aware of. So the motorcycle license, when you do the motorcycle license, you have to take a class that basically tells you that you are very likely to die riding a motorcycle. That's what they do. And in the US, it's very likely, right? Because it's all cars and trucks and lorries and stuff on the highway. Very few motorbikes. Very, very few motorbikes. And people do it for thrill. People ride motorbikes for thrill, not for... Here, why do people ride motorbikes? To get to where you want faster, right? Because your car is not going to get there. In Bangalore, if you're taking 2 hours to get to where you want your car, your motorbike will take you in 45 minutes, right? You can squeeze through traffic and get between cars. You can run the signal. You can do all of that. Huh? You can ride on footpath also. You can do all of that. So, but in the US, what they tell you, again, the idea of pitfalls. The first thing that they tell you is, oh great, you've bought a motorcycle. No. They say, you realize that you are much more likely to die now than when you have a car, right? And so you have to go to this class and you have to get a separate license, and then you have to sign off a few forms saying that I know all of those. And they give you a 3-hour class. 3-hour class on motorcycle riding, and that's a mandatory class, and half of that class is about blind spots. Right? Blind spots of not the motorbike guy, but the blind spot of the guys driving cars and trucks. Because if you are driving a motorcycle, you're very likely to be in the blind spot of a car driver or a motorcycle driver. So the whole thing is about pitfalls. It's not about how to ride a motorbike. That they know they know you know how to ride a motorbike. It's about pitfalls. That's exactly how research in using these advanced technologies have to be. Pitfalls. What is that which can go wrong? Right? Because go right, we always are looking for it. We know what you can get, but what goes wrong? So you should have that kind of a mentality where, again, in research, if you're doing research, question everything, right? That's the first thing. Question everything. Could be the stupid, dumb question, but question it. And when you start questioning, and question yourself, that's the important thing that you have. Self-criticism is the bigger thing. So if you don't want to be critiqued by a reviewer, criticize yourself. Look at, when you write a paper, think of what all are wrong in this paper. What all are possible mistakes. Think like a reviewer. What all can somebody point out as mistakes in this paper? Right? So that's a way to do, that's the only way to progress, right? If we are all comfortable, right, they all say progress comes from restlessness. Progress comes from being irritated. Progress, if everybody is satisfied with where we are, there won't be any progress. Now, there are two things, and I would like to do this because I have seen this from two sides. In life, you want to be content. You want to be happy. You want to be peaceful. In research, you want to be totally opposite. You never want to be content. You never want to say that, yes, I know it, it's enough. You never want to say that, I'm happy with my results. You never want to say that, okay, that's what it is, I'm satisfied. No, you will not make progress. So, balancing our split personalities, and a lot of people, so you see people, research, stressful, right? Why is it stressful? You're trying to deal with research like life, where you want peace, and you want peace in research also. No. Think of research as a process where you are irritated, you are restless, you are angry, you are agitated all the time. You love research. Right? Then that's the pattern of life in research. In real life, be the total opposite. Be content, be happy, be peaceful. Don't shout, don't be angry. Don't get irritated with people in life. But in research, do all of that. But not with others, but with yourself. That internal agitation, I call it the internal activation energy. You always have to have that internal activation energy, not to be satisfied with what you get. Again, when I say not to be satisfied, don't say that all results that I get is crap. But I say, okay, this looks good, what next? And my students always complain. They would work 6 months, do some wonderful stuff, and I know that they're working hard. But I don't want to tell them that it's a great job straight away, right? So when they come, Professor, we got this. So I'll just ask, what next? And I'll say, oh my God. 6 months I've been slogging to get this, and this guy immediately is asking, what next? Can I get a break for 2 days? No, that's not what I want to tell you. But what next? I know you've done this well. Maintain it, and what next? And that's where that curiosity, that intellect for students especially, that fire in the belly, right? Never leave. And a lot of people say, I'm done with research. I slogged for my PhD. No, you don't slog. So the other idea, if you are a bad teacher, for teachers here, don't worry, it's a good thing. Tell your students, it's a good thing that I'm a bad teacher. If I'm a really good teacher, you have life so easy. If I'm a bad teacher, you're forced to fish for yourselves. You will become much better because I was a bad teacher. Right? You don't have to, but it's something that you can use as an argument if you want to. Okay? Just because I'm a bad teacher, it made you better, right? You can always ask them. Okay. It's very warm here. Okay. What next? Thermogravimetry. So X-ray does identification of crystalline products. X-ray tells you what you have in the system. If there is something totally new that you think will form, X-ray will identify that. The thermogravimetry quantifies it. Okay? Thermogravimetric analysis quantifies, tells you how much of what is there in a system. Very, very, very simple idea again. If I form something, if I have a mass of something if I form something, if I give it a lot of energy, I can disintegrate that also. Right? I form something, I can disintegrate. Simple idea, calcium carbonate decomposes to calcium oxide and carbon dioxide at 700 to 800 degrees Celsius. calcium carbonate, CaCO3. If I look at my periodic table, I can calculate what is the molecular weight of calcium carbonate. Can somebody tell me the molecular weight of calcium carbonate without looking at any of these tables? How much? CaCO3. What is Ca? No, how much is, what's the atomic weight of calcium? 44. Carbon? 12. Oxygen? 16. Add all of those, how much? 44 plus 12, 56. No, 40. Which one? O3 is 48. Carbon is 1260. Calcium is 40. Right? Calcium is? Calcium is 44? Are you sure? Check it. Should you not get 100 overall for calcium carbonate? How much? 104? I'm not sure it's 104 or 100. Check your numbers. So if you know that, and then calcium oxide plus carbon dioxide, you know exactly how much carbon dioxide goes off. You know how much exactly mass is left. You can do a simple stoichiometric calculation and see how much is left. Okay. So you look at the rate and degradation of compounds. You can do absorb moisture content, you get amount of organic and inorganic compounds, you get reaction kinetics based on weight changes, all of that. So it's, all of you have seen a TGA instrument, most of you have seen a thermogravimetric analyzer? 40. Calcium is 40. So altogether gets you 100. And calcium oxide is 56, CaO is 56. 44 is carbon dioxide. 44 out of 100, 44% of mass is lost from what you have. You look at the curves and you know what that is. Okay, so thermogravimetry gives you, this is a sophisticated way of doing it.